So here we look at Chebyshev and Jacobi families of orthogonal polynomials. So the idea of orthogonality has been coming up a lot as we've been looking at the various special functions, be it Laguerre, Legendre, Hermite, and all of that. So Chebyshev and Jacobi families of orthogonal polynomials. Here we look at topics like Chebyshev polynomials, approximation theory, Jacobi polynomials, Gegenbauer polynomials, and of course the Rodrigues formulas, which we've seen in almost every case of special function we've considered. So let's look at the orthogonal polynomial families. Orthogonal polynomials are polynomial sequences that satisfy an orthogonality relation with respect to a weight function. So given an inner product fg, which is equal to integral from a to b of f of x, g of x, w of x dx, where w of x now is the weight function, while these two functions f and g would be the uh, polynomials whose orthogonality you're trying to check out. So w of x is the weight function. So and the interval is ab. So a sequence Pn of x is orthogonal if the inner product of Pn comma Pn is equal to 0 for n not equal to m. We've seen that consistently. These polynomials arise naturally in Sturm-Liouville theory, approximation theory, quadrature, spectral methods, and of course in mathematical physics. So straight up to the Jacobi polynomials. The Jacobi polynomials are denoted by P sub n power a alpha comma beta of x with parameters alpha bigger than -1 and beta bigger than -1 also defined on the interval the closed interval -1 to 1 with weight function w of x, which is 1 minus x alpha 1 plus x power beta, 1 minus x power alpha, 1 plus x power beta. So the Jacobi family is the most general classical orthogonal polynomial family. So it is the most general classical orthogonal polynomial family. So, and of course, just like we know already, you see things, you hear Jacobi functions or Jacobi polynomials are arising from as solutions to the Jacobi differential equations. So that's the pattern. Looking at Legendre, Laguerre, Hermite differential equations. When you solve them, you get the Legendre polynomials, you get Hermite polynomials and Laguerre polynomials and all of that. So Jacobi polynomials satisfy the second order differential equation, 1 minus x squared y prime prime plus beta minus alpha plus beta plus 2 multiplied by x y prime plus n into n plus alpha plus beta plus 1 multiplied by y equals 0. So, and this is a Sturm-Liouville problem. So, and then we see Rodrigues formula for Jacobi polynomials. So we've seen consistently that Rodrigues formula helps us to generate different levels of for different values of n, whatever polynomial you're looking for. In this case, we talk about the Jacobi polynomial. So the Rodrigues formula for that is P sub n alpha comma beta of x is equals -1 raised by n over 2 power n factorial into 1 minus x raised by minus alpha, 1 plus x raised by minus beta, dn dxn into 1 minus x raised by alpha plus n, 1 plus x raised by beta plus n. And this formula generates all Jacobi polynomials. And then we talk about orthogonality of Jacobi polynomials. So Jacobi polynomials satisfy integral from -1 to 1 of p sub n alpha beta x of x, p sub m uh, super alpha comma beta of x 1 minus x alpha power alpha 1 plus x power beta dx equals 0. So in this case now the weight function is like this 1 minus x raised power alpha 1 plus x multiplied by 1 plus x raised power beta and that is equal to 0 for n not equal to m. So, and then we have special cases. So, important special cases are as follows. You have many famous polynomial families are special cases of Jacobi polynomials. For instance, Legendre is the special case where alpha and beta is equal to 0. Chebyshev type 1 is the case of Jacobi where alpha equals beta, alpha and beta are both minus half. Then Chebyshev type 2 is when alpha and beta are both equal to half. Then Gegenbauer where alpha and beta are equal to lambda minus half. So those are important special cases. And that takes us to the idea of Chebyshev polynomials. So the Chebyshev polynomials of the first kind are defined by T sub n of x equals cos n into arc cos of x. So they are among the most important polynomials in approximation theory. So cos n arc cos of x. So first few Chebyshev polynomials include t naught of x, which is 1, t1 of x, which is x, t2 of x, which is 2x squared minus 1, t3 of x, which is 4x cubed minus 3x, t4 of x, which is 8x raised to power 4 minus 8x squared plus 1. And then we have the recurrence relation. Chebyshev polynomials satisfy the recurrence relation. T sub n plus 1 of x equals 2x t sub n of x minus t sub n minus 1 of x, with initial conditions t naught of x equals 1 and t1 of x equals x. I mean, just like what we've seen here. Then we have orthogonality of Chebyshev polynomials. So the weight function is w of x, which is equal to 1 over square root of 1 minus x squared. So the orthogonality relation then is integral from minus 1 to 1 of tn of x, tm of x, and the weight function is what you have here. 1 over, that's one square root of 1 minus x squared dx equals 0. So for n equals m. So this will go to 0. Then we have the Rodrigues formula for Chebyshev polynomials now. Rodrigues formula helps us to get uh, different terms of the Chebyshev polynomial. So the Rodrigues formula for Chebyshev polynomials of the first kind is t sub n of x, which is minus 1 raised to power n, square root of pi, 1 minus x squared raised to power half, all over 2 raised to power n, gamma n plus half, then dn dxn of 1 minus x squared raised to power n minus half. So, and then we have the geometric interpretation. So if you let x be equal to cos theta, then we say that t sub n of x is cos n theta. This explains oscillatory behavior. It explains extrema, roots, and approximation properties. Then we have the roots of Chebyshev polynomials. The roots are x sub k equals cos 2k minus 1 over 2n pi for k equals 1 to up to n. These are called Chebyshev nodes, like that. Then we have approximation theory. So approximation theory studies how well functions can be approximated by simpler functions. A function can be approximated by a polynomial f of x, which is approximately p sub n of x. So Chebyshev polynomials are optimal for polynomial approximation because they minimize oscillations near end points. So Chebyshev polynomials are optimal for polynomial approximation because they minimize oscillations near endpoints. So, and then we have the minimax property. So, among all monic polynomials of degree n, 2 raised by 1 minus n, t sub n of x has the smallest maximum absolute value on the interval minus 1, comma 1. That's closed interval. Now, this is called the minimax property. And then we look at the Chebyshev series expansion. A function can be expanded as f of x equals summation from n equals 0 to infinity for a sub n t sub n of x, where a sub n is 2 over square root of pi, integral from minus 1 to 1 of f of x t sub n of x all over square root of 1 minus x squared dx. This is analogous to the Fourier series. I mean, looking at this 2 over pi. So if you want to know more about Fourier series, you can check out the playlist on Fourier series on this channel. Then, so it means if we want to compute 3 sub x of 3, I mean t sub 3 of x using t sub n of x equals cos n arc cos of x, we can let x be cos theta, let x be cos theta. Then we say that t sub 3 of x will be cos 3 theta, t sub 3 of x, that's t sub 3 of x, that'll be 3 arc cos theta. Well, x is already cos theta, so we have this to be cos 3 theta. And now, so because x is cos theta here, yeah, so we have cos 3 theta. So because x is cos theta, it means that okay, that's cos theta, arc cos theta. So that cancels out. So we just have 3 theta. Yeah, that's the deal. Then using the trigonometric identity now, we see that cos 3 theta can be expressed as 4 cos squared cos cube theta minus 3 cos theta. Of course, that's you breaking it up like cos 2 theta plus theta and then expanding and doing it until you get all the cos out. In case you want to know more about trig, I have a playlist on trigonometry which you can check out to see all these identities. So in this case now we then obtain t sub 3 of x to be 4x cubed minus 3x because this is cos theta is x, right? So cos cube theta is x cube, cos theta is x. So that's t sub 3 of x is 4x cubed minus 3x. Then we have the idea of orthogonality. So you want to evaluate integral from -1 to 1 of t1 of x, t2 of x, all over square root of 1 minus x squared dx. Since t1 of x is x and t2 of x is 2x squared minus 1, orthogonality simply implies that if you put all of that together, you get 0. Okay? So it's more like you have x into 2x cubed minus 1 and you do all the maths and you're good to go. That gives you 0. Then let's talk about the Gegenbauer polynomials. The Gegenbauer polynomials are denoted by C sub n lambda x. They are orthogonal on the closed interval -1 to 1 with weight function w of x equals 1 minus x squared raised by lambda minus half. So the Gegenbauer differential equation, of course, the Gegenbauer polynomials will arrive from the Gegenbauer differential equation, which is 1 minus x squared y prime prime minus 2 lambda plus 1 x y prime plus n into n plus 2 lambda y equals 0. So, and then we also have the Rodrigues formula for Gegenbauer polynomials. So you have C sub n uh, lambda like that, and then of x equals minus 2 raised power n, gamma n plus lambda, lambda plus half all over n factorial, gamma n plus 2 lambda. Then you have 1 minus x squared, half minus raised by half minus lambda dn dxn 1 minus x squared n plus lambda minus half. So that's some serious issue there. So you have special cases of Gegenbauer polynomials. When lambda is half, you get Legendre. When lambda approaches 0, you get Chebyshev type 1. When lambda is 1, you get Chebyshev type 2. And then we have the family hierarchy. So for all this family of polynomials you have seen now, we have a hierarchy. We see that the hierarchy is that the Jacobi polynomials contain the Gegenbauer polynomials. The Gegenbauer polynomials contain the Legendre or Chebyshev polynomials. So the connection formula then is that the Gegenbauer polynomial is equal to 2 lambda sub n. But that's like Pokama symbol. Now, if you remember Pokama symbol, that's the fourth video in this series, I believe. All over lambda plus half sub n, then p sub n raised by lambda minus half of x, where a sub n is the Pokama symbol. So remember in Pokama symbol, 3 sub 4 means 3 times 4 times 5 times 6. So starting from 3, it goes 4 steps, starting with that 3. Then we have generating functions now. So Chebyshev generating function is summation from n equals 0 to infinity t sub n of x t raised power n, which is equal to 1 minus tx over 1 plus 1 minus 2tx plus t squared. And then you have the Gegenbauer generating function, which is summation from n equals 0 to infinity for c sub n lambda x t raised power n, which is equal to 1 minus 2xt plus t squared raised power minus lambda. And then you have the Gaussian quadrature. Orthogonal polynomials generates optimal quadrature rules. So for the polynomial, for Legendre, you have the Gauss-Legendre quadrature. For Chebyshev, you have the Gauss-Chebyshev quadrature. For Jacobi, you have the Gauss-Jacobi quadrature. So the roots of the orthogonal polynomial become the quadrature nodes. Then we have the Gauss-Chebyshev quadrature now. So the quadrature formula is integral from -1 to 1 f of x all over square root of 1 minus x squared dx, which is approximately pi over n summation k equals 1 to n f of x sub k, where x sub k is cos 2k minus 1 over 2n multiplied by pi. And then you have the Gauss-Chebyshev quadrature, for instance. If you want to approximate integral from -1 to 1, x squared over square root of 1 minus x squared dx using n equals 2. So the notes here will be you have cos pi over 4, which is root 2 over 2, and then x2 will be cos 3 pi over 4, which is minus root 2 over 2, like that. So in that case, you apply the quadrature formula, which is pi over 2 into, x1 squared plus x2 squared. So that'll be root 2 over 2 squared plus minus root 2 over 2 squared. So when you square this, you get 2 over 4. This also gives 2 over 4. That's half plus half, which is 1. 1 times pi over 2 just gives you pi over 4, like that here. So that's what you get. Then we can do some Python implementations. So generate Chebyshev polynomials. You just say from numpy.polynomial.chebyshev import Chebyshev. Then you have Chebyshev.basis 4. So this is T4 now. So you have T1 of x, T2. So everything just a 1.0 at the end of the day for T4 of x. So then you have you want to plot the Chebyshev polynomials also from -1 to 1. You have the Chebyshev basis and all of that. So you have this. I think we saw something about Chebyshev in the first video. So this is the blue line on line one. Then this other one is like uh something hanging from end to end of line one. And then you have the T2, which is green. So something like this, and then you have the red one just going and so on. So following each as they increase, you have patterns like that. Then you can have the Chebyshev notes too, where you have two within range 1 plus n minus 1 and all that. You have 0.98 and so on and so forth. So I think trying to, it's looking like there's some kind of symmetry, yeah? So you can see these values on the positive side are exactly this on the negative side. And then in fact, if you divide it, so plus, minus, plus, minus, plus, minus, plus, minus. So some kind of symmetry there, talking about the nodes. Then we have the Chebyshev interpolation. So for Chebyshev interpolation, so yeah, Chebyshev is a very powerful interpolation method, because it's kind of end to end like we saw before. So as you can see, if you imagine you have this original line and you try to interpolate using Chebyshev like this, so it's really cool. So this is how the code goes. So what we're interpolating here is the function 1 over 1 plus 25x squared. So using the SciPy interpolate, we carry the barycentric interpolator here, and then all the other steps go as you can see. So we then have the Jacobi polynomials here. So for the Jacobi polynomials over -1 to 1, we take alpha to be 0.5 and beta 0.5, and then we evaluate the Jacobi, and then we do the plotting, and we get something like this. So there's a bit of similarity between this and the Chebyshev one, like this blue one now with the line at 1. And then this one, of course, the n equals 1 is now a kind of line slanting like that. And n equals 2 is, like hanging end to end for 2 and so on. Then we have the Gegenbauer polynomials here. So you have this kind of arrangement too. And then we have the spectral methods. So Chebyshev polynomials are heavily used in spectral methods. A function is approximated as u of x equals summation from n equals 0 to n of a sub n t sub n of x. The coefficients are determined numerically to solve differential equations. Spectral methods often achieve exponential convergence for smooth problems. And we have a summary table right here. So we have the Jacobi family, and the weight function is 1 minus x raised per alpha multiplied by 1 plus x raised per beta. The interval is the closed interval -1 to 1. The Gegenbauer, 1 minus x squared raised by lambda minus half, same closed interval. Then Chebyshev type 1 is 1 minus x squared raised by minus half, same closed interval. And Chebyshev type 2, 1 minus x squared raised by half, same closed interval -1 to 1. So the final remarks we then see here are as follows. The Chebyshev Jacobi hierarchy forms one of the most important structures in classical analysis. These polynomial families provide exact solutions to differential equations, optimal polynomial approximation, numerical stability, Gaussian quadrature rules, spectral representations, and they are fundamental in numerical analysis, scientific computing, mathematical physics, approximation theory, and computational engineering. So we have some practice problems now. Um, Prove that the Chebyshev polynomial T sub n of x has degree n. Use the recurrence formula that to compute T sub 5 of x explicitly. So I'll just flash the problems like that. I'll flash the problems and then I'll decide the ones I'm going to solve. Yeah, I think I'll be taking care of 10 and 15. So watch out for 10 and 15. So here you have 1 to 5. Okay, even 1 to, okay, 1 to 4, everything 1 to 4 is showing for now. 1 to 4, then 5 to 5 to 8. We can see all of 5 to 8, like this 5 to 8. Then 9 to 13, or maybe 9 to 12. 9 to 12. So don't forget, I'll be taking care of question 10 and 15. So question 10, derive the generating function, this. So we want to derive this. Then next, I go for 12. Here you have 12 to 16. I'll be taking care of 15. We want to prove that Jacobi polynomials satisfy Pn alpha beta minus x equals minus 1 raised by n p and beta alpha x. Then the rest, 6 to, okay, maybe we can't see everything. 6, you can see 6 to 19 here. And then we can then see 7 to, okay, even 17, we can see, so you see 17, then we have 18 to 20. So let's go ahead and take questions 10 and 15 as we begin to bring this to a close. So problem 10, for starters, problem 10. So derive the generating function, summation from n equals 0 to infinity t sub n of x, t raised power n equals 1 minus tx all over 1 minus 2tx plus t squared. So step 1, start from the definition, right? So you'd recall, that t sub n of x is equal to cos n theta. Start from there, where you know that x is equal to cos theta. So then we have summation from n equals 0 to infinity t sub n of x, t raised power n equals summation from n equals 0 to infinity for cos n theta t raised power n. So using Euler's formula, we then have cos n theta equals e raised power I n theta plus e raised power minus I n theta all over 2. So that's Euler's formula there. Thus, we have summation from n equals 0 to infinity cos n theta t raised power n, which is equal to half summation from n equals 0 to infinity e raised power I n theta plus e raised power minus I n theta multiplied by t raised power n. So we split the series. So if we split the series, we have this part now to be equal to half into summation from n equals 0 to infinity, then t e raised power I theta raised power n plus summation from n equals 0 to infinity t e raised power minus I theta raised power n again. So afterwards, we can then talk about, we can then recall that summation from n equals 0 to infinity r raised power n is equal to 1 over 1 minus r. Okay, that's this works for if you want to look at it as sum to infinity and all that. So you have first term all over 1 minus first term, which is obviously when n is 0 here, that's 1. So first term over a minus common ratio, which is r. So that works here. And this works for absolute value of r less than 1. That's the convergence point. So therefore, we have that that whole expression, the right-hand side, right? This right-hand side, we have here, which was simplified to be this. So that right-hand side, yeah, can then be equal to half into 1 all over 1 minus te raised by I theta plus plus 1 all over 1 minus t e raised by minus I theta. Like this. So we have that done. And then we then go ahead to, so we then have to combine. So we combine over a common denominator. Combine over a common denominator. Okay. So we have that right hand side now is equal to 1 over 2, 1 over 2, then 1 minus t e raised by minus theta plus 1 minus t e raised by I theta all over 1 minus t e raised by I theta into 1 minus t e raised by minus I theta, like this. So, and that is equal to, so if we simplify the numerator, we simplify, right? We have, okay, that's numerator up here. We have 2. 1 plus 1 is 2. Of course, we still have half here, right? Okay, this 2 goes down. So if we simplify this, we have 2 minus, as 1 plus 1, 2, like this. Then minus t into e raised by I theta, e raised by I theta plus e raised by minus I theta all over 2 into 1 minus, when we expand all of this now, that'll be 2t cos theta plus t squared. You know, when we do all of that. So of course that's using e. So if we use e raised by I theta, so we can recall that e raised by I theta plus e raised by minus I theta is equal to 2 cos theta. That makes sense because this is cos theta plus I sin theta, cos theta plus minus I sin theta. So the plus or minus I sin theta will cancel out. So we have cos theta plus cos theta. That's 2 cos theta. So in that case, that means that the right hand side will now be equal to 2 minus 2t cos theta. All right, because this is 2 cos theta here. Then um all over 2 again, 2 into 1 minus 2t cos theta plus t squared down here. So what do we do? 2 is common here. So we have the right hand side is equal to 2 into 1 minus t cos theta all over 2 into 1 minus 2t cos t plus t squared. This cancels out. So we have the right hand side to be equal to 1 minus t cos theta all over 1 minus 2t cos t plus t squared. That's the right hand side. So, and since x is equal to cos theta, right? Then we can then have the generating function. The generating function becomes this now. It becomes summation from summation from n equals 0 to infinity t sub n of x t raised power n equals, because x is cos theta is x. So 1 minus t cos theta, that will be 1 minus tx. We have 1 minus tx all over, down there, we have 1 minus 2tx, because cos theta is x, that will be 2tx plus t squared. So this is finally the generating function for uh, the case we are considering. That, yeah, so that generating function which we have to derive, that's the original problem now. So we have to derive this, and we have done that by, by recalling that t sub n of x is cos n theta, and then doing the Euler stuff and we keep expanding the right-hand side until we get that expression. Okay, so that takes us to problem 15. So for problem 15 now, we're expected to, so problem 15, we want to prove that Jacobi polynomials satisfy, I want to prove that they satisfy P sub n alpha beta up there of minus x is equal to minus 1 raised power n, P sub n, then beta alpha of x. So you see the sign shifting now. Minus x here, the sign shifts to minus 1 raised power n, and then alpha beta is swapped to beta alpha. So let's go and see how that works. First of all, we start with the Rodrigues formula. So you remember that the Rodrigues formula for Jacobi polynomials is P sub n alpha comma beta of x equals minus 1 raised power n, 2 raised power n, n factorial, then 1 minus x raised power minus alpha. Then I need to shrink this for space. Then 1 plus x raised power beta, then dn dxn into 1 minus x raised power alpha plus n, 1 plus x raised power beta plus n, like that. We now replace x by minus x. So we already have this. So if we replace x by minus x, so this is the Rodrigues formula, right? So here now, it's more like this x now becomes minus x. So let's see what that looks like. So if we replace x by minus x, we then have p sub n alpha comma beta minus x equals, so minus x, right? So from this expression, so anywhere we see x, we put minus x. So we then have this now, minus 1 raised power n, that remains, 2 raised power n, n factorial. Then here, x is now minus x. So we have 1 plus x raised power minus half. Then 1 plus x here becomes, this 1 plus x here becomes 1 minus x. So we have 1 minus x raised power beta dn dxn into 1 minus x here becomes 1 plus x raised by alpha plus n, alpha plus n. Then here we have 1 minus x beta plus n. Okay, so every x has now become minus x. So with that in place, we can then have, we need to differentiate here, I think. So, and then this is a function of x, this is also a function of x. We need to use chain rule. So using the chain rule, we know that d of d minus x is equal to minus d dx. Okay, using chain rule. So if that is the case, you can say therefore dn d minus xn is the same thing as minus 1 raised power dn dxn. So we have that, and that's because we are paying attention to this part which we need to differentiate. So that will be minus 1. So it is minus 1 raised power n dn dxn. Talking about differentiation. So substituting this into the expression gives, so that gives us p sub n, p sub n alpha comma beta minus x equals minus 1 raised power n, 2 raised power n, n factorial, 1 plus x raised power minus alpha, 1 minus x raised power minus beta, then now minus 1 raised power n, dn dxn into 1 plus x raised power alpha plus n, then 1 minus x raised power beta plus n. So since we have minus 1 raised power n, minus 1 raised power n to be minus 1 raised power 2n, which is equal to 1, then we obtain, so because now we have minus 1 raised power n here and another minus 1 raised power n here. So putting all of that together, that means we have this two put together will become 1. So then we then obtain p n alpha comma beta of minus x here equals, so 1 over 2 raised power n, n factorial, 1 plus x raised power minus alpha, 1 minus x raised power minus beta, then dn dxn into 1 plus x raised power alpha plus n, and 1 minus x raised power beta plus n, like that. So next thing now, we can compare with the Rodrigues formula for, so now write the Rodrigues formula, for p sub n beta comma alpha of x. So beta comma alpha sub x. So that's simply, so that is p sub n beta comma alpha of x. That will simply be minus 1 raised power n all over 2 raised power n, n factorial, 1 minus x raised power minus beta, then 1 plus x raised power minus alpha, then dn dxn into 1 minus x raised power beta plus n, then 1 plus x raised power alpha plus n, like that. So multiplying both sides, multiplying both sides by minus 1 raised power n will now give us gives minus 1 raised power n p sub n beta comma alpha of x equals 1 over 2 raised power n, n factorial, then 1 minus x raised power minus beta, then 1 plus x raised power minus alpha, then dn dxn, 1 minus x raised to power beta plus n, then 1 plus x raised to power alpha plus n. So we see that this expression, this expression is exactly identical, to the one obtained for p sub n alpha comma beta of minus x. So that means they are the same. So we can conclude now that we can say hence p sub n alpha beta evaluated at minus x is simply the same thing as minus 1 raised to power n, then p sub n beta comma alpha evaluated at x, which proves the symmetry relation. That's what we are required to prove, the symmetry relation. And with that, we come to the end of this video talking about Jacobi and Chebyshev of families rather of differential of orthogonal polynomials, yeah, of orthogonal polynomials. So I'll flash the questions again and then we call it a date. So you have questions 1 to 4 here, then 5 to, okay, I need to shrink this, 5 to 9, then 10 to, I did question 10. So you have 10 to 14 right here. Then you have 15. I did 15 also. So you have 15 to say up to 19, but now 16 to 20 here. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you haven't subscribed, why not go ahead and do that right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges, which you'll find out as you click on join. Um, ultimately, don't forget to comment, like, share, so that you can always get alerted, so that other people rather can also be aware of this great content I have going on here. Till I come your way again, keep doing maths right. Bye.